this lesson, we're going to be talking about all the properties of rational exponents and of radicals. So all of this is just a review for you, but I'm going to give some examples out to the side just to kind of refresh your memory. So we have the product of powers, which states that if I have like 2 to the third times 2 to the second, if those bases are the same that I'm multiplying, then I can keep that base of 2 and just add those exponents together to make 5. Okay. The product of a power states that if I have a number raised to a power, let's say 2 to the second, and then I raise that to another power, so a power raised to a power, then that would be the same thing as 2 to the multiply those two powers together to make 6. All right, the product power of a product, so let's say that I have 2 times 3, and I raise that to the fourth power. That's the same thing as saying 2 to the fourth times 3 to the fourth. That is not the same as when you have a plus sign there. Okay, it has to be multiplication. And then we talked about negative exponents in the last lesson where you flip the base, right? And then that makes the exponent positive. Zero exponents, when you raise something to the 0 power, it's always 1. And the quotient of powers, which is kind of like the product of powers, if I have like 4 to the second divided by 4 to the third, I would take the top exponent and subtract the bottom. So that would be 4 to the 2 minus 3, which is 4 to the negative 1, and then I would take care of that. All right? And then the power of a quotient, which states that if I have, say, 2 over 3, and I raise that to the third power, I can take the top number and raise it to the third power, and then take the bottom number and raise it to the third power. And these all work backwards as well. So if I had this and maybe this was a 6 and a 3 and they divided, I could say 6 over 3 raised to the third power. So you can work backwards on that as well. So there's a little bit more explanation. So these are things that we use anyways all the time, right? We've used these all along the way. So we are just going to simplify these. We're not necessarily going to actually work them out completely. I just want to make sure that we can put things together properly. So notice that you're multiplying two things that have the same base, so you will keep that base of 7, and you will add the exponents. So I'm going to add the 1/4 and the 1/2, and I'm actually going to write that as a step. That way when you look back at these notes, that will be there, and you can be like, oh yeah, that's where that came from. And so that would be 7 to the 3/4. And like I said, we're not going to finish them out. We're going to leave them that way. So 7 to the 3/4. All right, if you look at these, like my first instinct is to want to try and put these together. But I can't put them together as one because they have different bases, right? So instead, I notice that I'm raising two separate things to a power here. So I'm going to take each one individually and raise them to that power. So 6 to the 1/2 to the second power times 4 to the 1/3 to the second power. I'm pretty much just distributing this power of 2, right? So then when I have a power and I raise that to another power, I multiply those together. So that would be 6 to the first power, so I don't need to put that up there, times, and then I would take the 1/3 times the 2, so that would be 4 to the 2/3. And since I can't put these together, I'm just going to stop right there. All right, now we talked yesterday about that negative exponent. I don't like that that's there, right? And I could go ahead and distribute right here if I wanted to, but then I'm going to have two negative exponents instead of just the one. So I'm going to take care of this first. So I have to take that base, and I have to flip it, right? That's what's going to make this exponent change to a positive. So that would give me 1 over 4 to the 5th times 3 to the 5th, all raised to the positive 1/5 power. Now, if I take 1 and I raise that to the 1/5 power, I just get 1. And then this is exactly what we had up here, right? Two separate things being multiplied raised to a power. So if I have 4/5 and I raise that to the 1/5 power, I would take the 1/5 times the 5, so that would just leave me with 4 to the first. And then same thing here, 3 to the 5th to the 1/5 would be 3, and then that's simple, so 1 over 4 times 3, which is 12. Now when I take a look at number 4, I notice that the base on top is the same as the base on bottom. So since I'm dividing two things with the same base, I'm going to subtract the exponents. So this has an exponent of 1, so I would keep the base of 5, and then I'll take the exponent in the top, which is 1, and subtract the exponent from the bottom, 1/3, which gives me 5 to the 2/3. Now, my formatting on number 5 is a little wonky. It wouldn't let me put bigger parentheses, so I'm just going to make this a bigger parenthesis right there. All right, so we don't have the same bases, right? But I do notice that I have a top being raised to a power and a bottom being raised to a power. So if I take 42 to the 1/3 and I raise that to the second power, that gives me 42 to the, multiply those together, 2/3. And then on the bottom, I have 6 to the 1/3 to the second power, so I'll multiply those again. And I have 6 to the 2/3. Now remember that quotient of powers property. I have two things being divided, but they both have the same exponent, right? So I can kind of do that one backwards and say this is the same thing as 42 over 6 to the 2/3, right? And the only reason I really want to do that is because 42 will divide by 6, right? 42 divided by 6 is 7, and then we have that raised to the 2/3. So we have fully simplified it. All right, so we have the product property, which we already know about that as well. Let's say that I'm taking the fourth root of 3a. I could separate that into two roots, right? I could do the fourth root of 3 times the fourth root of a. We have done those when we split square roots, right? And same thing with taking a root of a fraction. Let's say I did 3 over a. I would split that into the fourth root of 3 over the fourth root of a. All right? So we have simplified square roots, and now we're going to simplify larger roots, okay? So the first thing I always like to do when I'm simplifying roots is I'm going to check and just see if this is a perfect cube. Okay, it takes 5 seconds to plug into your calculator, and sometimes you can actually, save yourself some trouble if you actually check them. Neither one of these are perfect cubes, so I'm going to go ahead and multiply them together. So I'm just going to take and multiply the 12 and the 18, and we'll write that as a whole step. That way we don't forget when we look back at our notes. So I'm multiplying these two. They're the same root, so I can multiply them together. So the 12 times the 18 is going to give me the cubed root of 216. And the cubed root of 216 is 6. And we're done. Same thing with the ones that are being divided. If 80 is a perfect fourth root, I should take care of that right now, okay? It's not, and 5 is not a perfect fourth root either. But I do know that 80 will divide by 5, right? So I can work backwards and do one big root over 80 divided by 5. That gives me the fourth root of 16, which is 2. So 4 is not a perfect cube. Neither is 128. So I'm going to go ahead and multiply them together, but this time I'm actually not going to write it as a step. I'm just going to multiply them. 4 times 128, that gives me 512. And then the cubed root of 512 is 8. All right, 192, not a perfect fifth root. 6, not a perfect fifth root. So I'm going to go ahead and combine them into 1 because 192 will divide by 6. 192 divided by 6 is 32, and the fifth root of 32 is 2. So just like when we were to reduce roots that weren't perfect squares, right? We would be looking for ways we could write something using a perfect square, right? So what kind of exponents signified that they were perfect squares? Like if I had written like y to the 8th or y to the 9th or y to the 11th, how would you know which of these was a perfect square? Even numbers, because they all divide by the root number, right? So we always take that exponent and we divide it by the root number, right? And if they divide evenly, that means that they were a perfect square root, right? So if you were looking for things that were perfect cube roots, what kind of exponents would you be looking for? Numbers that would divide by 3, right? Or if you wanted a perfect fourth root, you would need exponents that were numbers that divided by 4. So we're going to go ahead and do a factor tree for 135, because 135 is not a perfect cube. You should always check that right in the beginning, though, just to make sure. So 135, that will divide by 5. That's 5 and 27. 5 is perfect square, or 5 is a prime number. 27 divides by 3, so 3 times 9. 3 is a prime number. And 9 is 3 times 3. So if we wrote this out, this would be 3 to the third and then 5 to the first, right? Now, this is obviously a perfect cube root, right? And this right here, this power is less than 3, which means you can't split this any further, right? So this is the number that will be left under your root. This is your perfect. So you have the cube root of 3 to the third times the cubed root of 5. The cubed root of 3 to the third is 3, and then you have your cube root of 5 at the back. And something I have not mentioned, please make sure that your root number here, your index, that is in the crook and that it is smaller. Okay, otherwise I get confused as to what that number means. All right. Now, if I look at these two right here, I'm going to assess first. 7's a prime number, right? So it definitely can't be split into anything useful as a fifth root. And 8 is 2 times 2 times 2, right? So I don't have 5 or more of any prime number. Also, 7 does not divide by 8 at all, right? It doesn't reduce or anything. So I have a problem. I can't get rid of this root off the bottom in my given state. So somehow, I have to make a perfect root on the bottom, a perfect fifth root. So I need to figure out a number I could multiply by 8 that would give me a perfect fifth root. So this is how I normally do that. I normally take the smallest number, and I raise it to whatever this root number is, 5. So 2 to the fifth is 32. So this is the smallest perfect fifth, all right? Will that 32 divide by 8? Yes. What is 32 divided by 8? It's 4, right? So I know that if I take 8 times 4, that gets me 32. So I'm going to multiply by the fifth root of 4 on top and bottom. Now remember, we do it on top and bottom because anything divided by itself is 1. And if we're multiplying by 1, we're not changing the value. We're just rewriting it, right? So the fifth root of 7 times the fifth root of 4, I just multiply those together. That gives me the fifth root of 28. And then I multiply in the bottom. The fifth root of 8 times the fifth root of 4 is the fifth root of 32, which should be a perfect fifth root, correct? And what is the fifth root of 32? It's 2. It should always be whatever number you raise to that fifth power, right? So on top, I have the fifth root of 28, and on the bottom, I have 2. All right, on number 12, if we look at 500, that's not a perfect cube, so we're going to do our factor tree here. So 500, I know that divides by 2, so 2 and 250. 2 is prime. 250 also divides by 2, so 2 times 125, 2 is prime. 125, that divides by 5, 5 and 25. 5 is prime, and then 25 is 5 times 5. So if I write this out, this is 5 to the third, which makes a perfect cube, right? And then times 2 to the second. Now, this power of 2 is smaller than my root, correct? So I know that that will just stay the same. So I have the cubed root of 5 to the third times the cubed root of, now I'm not going to put 2 squared in there because it's going to get left. So instead, I will just say 4. And then the cubed root of 5 cubed is 5. And then my cubed root of 4. All right, so number 13, we're going to assess here. I know that 19 is a prime number, so I can't split that into anything that I could reduce this root with. And 4 is 2 times 2, so I don't have 4 or more of any prime number. So I'm going to have to figure out a perfect fourth root. So we'll start with 2 to the fourth, which is 16. Does 16 divide by 4? Yes. So if I want to get a 16 on the bottom, I would need to multiply by 4. And I'm going to do that on the top as well. So if I take the fourth root of 19 times the fourth root of 4, I get the fourth root of 76. And then the fourth root of 4 times the fourth root of 4 is the fourth root of 16, which should be a perfect fourth root because that was my goal. So on top, I'm left with the fourth root of 76. And on bottom, what is the fourth root of 16? 2. If you've made your list, you should be able to look right there, and it's that number you're raising to the power. If not, you can plug it into your calculator too, right? Okay, and then I'm done with that one. All right, so I'm going to assess here 7 is prime. So I know that, well, 7 over 4, that doesn't reduce, right? So I'm going to have to cube root the top and the bottom. 7 is a prime number, so I can't split that into anything that I could reduce. And 4 is 2 times 2, so there's only 2 of those, not 3 or more. So I've got the cubed root of 7 over the cubed root of 4. So I'm trying to get a perfect cube on the bottom. This one would actually be kind of easy if you were thinking about it. But the smallest perfect cube we have would be 2 to the third, which is 8. Does the 8 divide by 4? Yes. So I want an 8 on the bottom. That means I would have to take this 4 times 2. I'm going to do that on top and bottom. 7 times 2 gives me the cubed root of 14. And then on the bottom here, you're going to get the cubed root of 8, right? Which is 2. Now, if you need to write that out as a step, maybe that this is the cubed root of 8. Okay? It's really not necessary because wasn't that the point? Like, that's why you did that, to get the 2. All right, so 1296 does not divide by 25. And 25 is 5 times 5, right? So I can't, do anything with that. So I'm going to fourth root the top and the bottom. Now, I always have you check to see if they're perfect fourth roots. I already checked the 25. Is 1296 a perfect fourth root? The answer to that is yes. Here's the thing. That's a big number, so it would definitely need a factor tree, right, to simplify it. You always want to simplify before you start working out. Otherwise, you have to simplify later with bigger numbers. The fourth root of 1296 is actually 6. So that actually helps us out a lot, right? So I've got 25 on the bottom, and I'm looking for a perfect fourth root. So I'm going to start with 2 to the fourth. So 2 to the fourth power is 16, right? Will 16 divide by 25? No. So I know that that one's not going to work. So now I'll do 3 to the fourth power. So 3 to the fourth power is 81. Will 81 divide by the 25? No. All right, so I will try 4 to the fourth power. 4 to the fourth power is 256. Does 256 divide by 25? No, so it's not 256. So I try 5 to the fourth. 5 to the fourth is 625. Does that divide by 25? Yes. So this is going to be the perfect fourth root that I want on bottom. So I'm going to multiply by the fourth root of, what is the 625 divided by 25? 25, right? 25 and 25, that will give me the 625. So I do that on top and bottom. Now I can't take the 6 and the 25 and multiply them because this does not have a fourth root on top of it, right? So I just smash them together. And then what do you get when you take the fourth root of 25 times the fourth root of 25? You get the fourth root of 625, which is 5. Make sure you can't reduce right there. And then you are finished. All right, so we're familiar with conjugates because we did them when we had i's, right? Like if we had a plus bi, then we also had a minus bi. Okay, we need this because when we have like a root on bottom, but then we also have it attached to like 5, so like 5 plus the square root of 3, I need a conjugate to get rid of that. So when you only have one root, you're going to change the sign in front of that one root. If you have two roots, then you have to change the sign that's in between them. All right, so I've got 5 plus the square root of 3, so I'm going to multiply by 5 minus the square root of 3 on top and bottom. And then we're just going to multiply. So if I take 1 times 5 minus the square root of 3, that gives me 5 minus the square root of 3. Then I'm going to multiply the bottom. So I have 5 times 5 is 25. 5 times a negative square root of 3 is a negative 5 square roots of 3. The square root of 3 times 5 is a positive 5 square root of 3. And then the square root of 3 times a negative square root of 3 is negative 3, right? Because the square root of 3 times the square root of 3 is 9, which is 3. All right, these two middle terms should always be the same but opposite signs because they're going to end up canceling. We don't want the root in the bottom. That's the whole point. So on top we have the 5 minus the square root of 3. On the bottom, the two middle cancels, and you have 25 minus 3, which is 22. And then you want to make sure that you can't reduce that in any way. 5 does not divide by 22, and plus you have a 1 right here that doesn't divide by 22 or reduce, so I'm done. Now on number 17, your root's in the wrong spot. You always want it to be the second one, so I'm going to rewrite this and put the negative 2 in the front and the positive root 7 at the back. If you don't do that, you end up changing the wrong sign, right? When you just have one root, you want to change the sign that's in front of the one root. So I'm going to multiply by the conjugate, which would be negative 2 minus the square root of 7 over negative 2 minus the square root of 7. So on top, 1 times all of that would be all of that that's on the top. On the bottom, we'll multiply that. So negative 2 times negative 2 is 4. Negative 2 times a negative square root of 7 is a positive 2 square root of 7. Square root of 7 times negative 2 is negative 2 square root of 7. See how we have the opposite signs right there? That's what we want. And the square root of 7 times a negative square root of 7 is negative 7. So on top, we have negative 2 minus the square root of 7. On the bottom, the two middle ones cancel, and 4 and -7 add together to make -3. I don't like negatives in the denominator like that when you just have one term down there. So just change all of the signs that you have. So this -2 changes to a +2. This -7 changes to a +7. And the -3 on bottom changes to a +3. On number 18, the conjugate of the bottom would be 6 plus the square root of 2. So I'm going to multiply top and bottom by that. So 3 times 6 gives me 18. And 3 times the square root of 2 is 3 square roots of 2. On the bottom, 6 times 6 is 36. 6 times the square root of 2 is 6 square roots of 2. -2 square root of 2 times 6 is -6 square roots of 2. Opposite signs, see? And then negative square root of 2 times positive square root of 2 is -2. Also, have you noticed that term at the back is always negative, right? Because you have opposite signs. So I have 18 plus 3 square roots of 2 on the top. These middle terms cancel. 36 and -2 make 34. And then I would just make sure that I couldn't reduce the 3, 34, and 18. I cannot, so I am done. On number 19, you have 2 square roots, so we're just going to change the sign in the middle. So we've got the square root of 10 plus the square root of 2. Same thing on the bottom. So the square root of 7 times the square root of 10 gives me the square root of 70. And the square root of 7 times the square root of 2 gives me the square root of 14. Then we multiply the bottoms. Square root of 10 times the square root of 10, that gives me the square root of 100, which is 10. Square root of 10 times the square root of 2 is the square root of 20. Negative square root of 2 times the square root of 10 is negative square root of 20. See that? Opposite signs. And negative square root of 2 times the positive square root of 2 is -2. So on the top I have the square root of 70 plus the square root of 14. On bottom, the two middles cancel, and 10 and -2 make 8. And I can't reduce, so I'm done. All right, so this, again, we're doing the same thing with the cubes, except now we're adding in a variable. So focus on the number, and then focus on the variable. So first, always check to see if this is a perfect cube. 64, is that a perfect cube? Yes. The cubed root of 64 is 4. And is y to the 6th a perfect cube? Does this number divide by this number? Yes, so it is. That would be y to the 2nd, because you got to take the 6 divided by the 3, right? So they were both perfect cubes. That makes it nice. All right. So if you look at these, what do you notice about both of these? The number on top, that's a perfect cube, yes. This is a perfect cube, so, or not cube, sorry, 4th root. So I'm going to take this 4th root of the top, and I'm going to take the 4th root of the bottom. What is the 4th root of x to the 4th? X. And the 4th root of y to the 8th? So y to the 2nd, and then I'm done. All right, so let's split this up into the cubed root of 27 and the cubed root of q to the 9th. So 27, that is a perfect cube. So the cubed root of 27 is 3. And what's the cubed root of q to the 9th? Q to the 3rd. On 23, what do you know about both of these? They are perfect 5th roots. So let's just figure it out. What is the fifth root of x to the 10th? X to the second. And what is the fifth root of y to the 5th? Okay, so I did several that were perfect, and I'm actually going to add in two problems here. All right, we'll call this 23a. The cubed root of 54 y to the 10th. So I'm going to do the cubed root of the 54 and the cubed root of the y to the 10th. 54 is not a perfect cube, so we're going to do a factor tree for that. So 54, that's 2 and 27. 2 is prime. And then 27 is 3 times 9. 3 is prime. And 9 is 3 times 3. So that gives me 3 to the third times 2. So this is my perfect cube. And then this power is less than the root, right? So this will be one that stays underneath. So that's the cubed root of 3 to the third times the cubed root of 2. Then we have to focus on our variable. So you need to split this into two things, right, where one of them will divide by 3, and the other one ends up being less than 3. So what you want to do is look at this number right here and just work your way down. So like the next lowest number is 9, right? Does 9 divide by 3? Yes. So I would use y to the 9th, which means how many will be left over? One of them, right? And I just want to point this out. Let's say you had used y to the 6th. How many y's would that leave? 4, right? But 4 is still bigger than 3, so you have to split this one again, right? So you want to take the biggest number, or the biggest number that's smaller than the 10, right? So out of these 4, which ones are your perfect cubes? The first one and the third one. So I've got the cubed root of 3 cubed is 3. The cubed root of y to the 9th is y to the third. And sometimes you might want to mark them out to be like, hey, I'm done with those. And then the leftover parts would be the second and the fourth one. And I'm just going to multiply them together underneath. So 2 times y. All right, and then let's call this 23b. All right, we'll do the cubed root. We'll do another cubed root. Cubed root of 3,888 x to the 11th. So let's start with the 3,888. We'll do a factor tree. So I know that that divides by 2. So we have 2 times 1944. I know that divides by 2. So 2 and 972. And I know that divides by 2. So 2 and 486. And I know that divides by 2. 2 and 243. Okay, that does not divide by 2, but it does divide by 3. So I divide it by 3, and you get 3 and 81. 81 also divides by 3. It's 3 and 27. 27 is 3 times 9, and then 9 is 3 times 3. That gives you 1, 2, 3, 4, 5 3s and 4 2s, right? And if you look at the exponent on both of those, they're both bigger than 3, correct? So if I were to split this up, I would think about this. Does 4 divide by 3? Does 3 divide by 3? Yes. So 3 to the third would be my perfect. And how many 3s would I have left over? 2 of them. All right, do the same thing with your 2 to the fourth. How many of those can I use to make the perfect cube? 3 of them. And how many will be left over? Okay? So I have 1, 2 left. So this one is a perfect cube, and this one is a perfect cube, which means these two get left underneath. All right? So when I write these down, I've got the cubed root of 3 to the third times the cubed root of 2 to the third. Those are my perfects. And then I'm actually going to go ahead and multiply these together. 3 squared is 9, right? And 9 times 2 is 18. There's the number underneath. Then look at your variable. It's 11. What's the biggest number that's smaller than 11 that you can divide by 3? 9. So I'm going to use x to the 9th, which leaves how many x's left over? 2 of them. So your perfects are the front one and the third one, right? Now when I cube root this, I have to do each one. So the cubed root of 3 cubed is 3, and the cubed root of 2 cubed is 2. So 3 times 2 gives you 6. So I'm done with that one. What's the cubed root of x to the 9th? X to the third. And then for the part that's left underneath, you have the 18 and the x squared.